Welcome to the next lecture of Mechanics of Material. This is Salman, Assistant Professor, ISL College of Engineering. So last class we have discussed about the few topics like thermal stresses, superposition of various forces acting, and similarly we have discussed about how the composite materials behave when we are acting upon thermal stresses. So in this lecture we are going to discuss about a strain energy. What is strain energy? How we are going to solve the what are the various types of strain energies because of various types of loadings, and how the problems has to be solved. So what is first of all the strain energy? For example, this I can explain you in a beautiful way is that if you consider a spring, if you are stretching or if you are compressing a spring, best example you can take it as compressing. If you are compressing your shock absorber, so when it is completely compressed and if suddenly removes the load, so it will release the whole energy. So what the spring is generally doing is it's trying to store some amount of energy in it. After the removal of the energy, it will give back the energy. So with what energy you have tried to store, compress it, the same energy will be released to make the spring open. Similarly, when strain energy is nothing but the amount of energy stored in a material when you are trying to give some load within elastic limit. For example, I am taking a rod, I'm trying to stretch it, but I have not gone to plastic deformation. It is still under elastic deformation. The very important thing in strain energy is it should be within the elastic limits. It should be within the elastic limits. For example, we have already discussed about the stress strain diagram. So if I consider the stress along y-axis and strain along x-axis, for every stress there is some amount of strain. We have already known that till some extent it will be having a linear graph. So during this linear graph, if I am trying to give the energy, it will be trying to store that energy in it. Okay, so this is also nothing but called as the work done within the elastic limit. So how much amount of work you are doing on a material to give some enlargement to it. For example, within the elastic limit you are applying load, it is going to get stretched. So for doing that stretching, how much amount of energy you have given. So generally the strain energy is nothing but the area enclosed within the elastic limit. So whatever is the area enclosed within the, for example, I am studying strain energy to till this extent. So then what is the area covered is nothing but this is the area should be always in mathematics. You might have studied areas under the curve, that is integration. So you might have studied that area should be considered only below the curve. So this is the only below the curve. So it's completely seems to be like a triangle. So if we know that the area under the curve is nothing but this, so what is the area? Nothing but half into sigma into E. So that is nothing but half into stress into strain. But whereas this V is nothing but, since we are considering strain is nothing but the rate of change of length to original length. So since we are dividing with length and here we are dividing with area, so area into length is nothing but the volume. So basing upon the volume, the amount of strain and the amount of stress is dependent. For example, if I am considering a very thick rod, so the basing upon the thickness you have to do more amount of stress has to be given. Similarly, if the area is less, the amount of stress given will be less, but whereas the elastic limit for the material will be same. So basing on that, you have to define that you have to consider the strain energy is equal to half into sigma into A, where is this is the area of the triangle and this is given for simplification. That is nothing but whatever the length and the volume with area which you have divided, that is compensated basing upon the material here. So strain energy is also called as resonance. So resonance is the total strain energy stored in an object when applied within the elastic limit. Sometimes resonance is also called as the capacity of a strain body for doing work. Nothing but when you are trying to do some amount of work, how much amount of strain it is going to absorb, that is called as resilience. The next thing is proof resilience. So proof resilience is nothing but the maximum stress within at elastic limit. So this is within elastic limit means, for example, if you are having this graph, so within elastic limit nothing but below this at any point, below this at any point. But whereas proof resilience is nothing but exactly at this point, exactly at this point. So for example, if you dot different curves, so this is the curve for proof resilience. So similarly for resilience or strain energy, it can be based upon the type of stress you have applied. It can be the total curve or it can be the curve till here. So that I am trying to highlight here. Let us show you, okay, so that you can clearly visualize. So this is nothing but the stress at the elastic limit, strain at the elastic limit, and the volume of the material. Clear? So proof resilience and resilience are two different things. Resilience is within the elastic limit, but whereas proof resilience is exactly at the elastic limit. Next is modulus of resilience. When I say modulus, you should divide it with unit volume. Proof resilience per unit volume is generally called as modulus of resilience. So now what is modulus of resilience is exactly nothing but the area under the curve of the stress and strain. So here if you see what is proof resilience, we have seen half into E sigma E. Sigma is nothing but the sigma at elastic limit, strain at elastic limit, and the volume of the material. Similarly, what is volume? So this I was highlighting here. So if it is proof resilience, then the resilience will be either it can be here, either it can be till here. So either can be this small this curve or this triangle. So basing on the type of sigma you have given. Okay, so now the proof resilience is till elastic limit, means total curve has to be considered. So modulus of resilience, we generally write the formula half into sigma E into elastic E, that is nothing but sigma at elastic limit and strain at elastic limit. This you have to remember. Now strain energy is generally denoted by a symbol U. Now let us try to try to take the what we say dimensions of this. So for example, what are the dimensions of stress? Is nothing but we already know the units of stress is nothing but Newton per mm square, that I have already drawn here, Newton per mm square. Strain is having no units, but whereas volume is having millimeter cube. Okay, so what is the unit of strain energy? Is nothing but Newton per mm, Newton per mm, Newton per Newton mm. It's Newton mm. So now when we are going to study about strain energy, the loads which I am giving to get the strain, it can be done in any way. Either you can apply the load gradually, either you can apply the load suddenly, either the load can be an impact load. So this energy which is going, for example, if you are driving a vehicle, the spring or suspension which you have backside, that can be happen in a different way. One is the person who's sitting behind your the second person, he can apply the load gradually, means while he is stepping in the vehicle, he can apply the load gradually and he sits on the back seat. So then the spring will be compressed to some extent. Suddenly you are moving and some damps are coming, so then sudden damping is happening, that is called as sudden load. And impact is nothing but you are going to apply the sudden brake, that is called as impact. So the spring which you are having in your suspension, it can have three different types of load. One is gradual load, another is sudden load, another is impact load. So among these loads, how the strain energy formulas are going to change, so how the stresses are going to differ, that we are going to see. So these are the few small what we say derivations which are very easy. The only thing you have to understand in this is nothing but the strain energy will be always equal to the amount of work done for getting the deformation within the elastic limit, always within the elastic limit. In strain energy, you should not go beyond the elastic limit. Okay, the strain energy when the load is applied gradually, obviously the stress strain curve which we have studied till date is all are the loads are applied gradually, step by step, that's why the curve is coming to be a straight line. Now what is the strain energy? Is nothing but the total area under the curve. Clear? So what is the area under the curve? Is nothing but half into stress into sigma into volume that you have got for strain energy. That is for one part. But whereas what is the amount of work done in doing this? For example, this is your rod. So for this, you are doing some work because of which this rod has been expanded to some length within the elastic limit. It has got expanded. So what is the amount we have done? Amount of work was done is nothing but force into displacement. Already in mechanics you might have studied this. Work done will be always nothing but the force into displacement. For example, if you are carrying some amount of force on your head and you are not moving, you are still standing at that position, then the amount of work done on that object is 0. Okay, and similarly, if you are having an object on your head and you are completing a circle and coming back to the original position, then the displacement is 0, so the work done will also be 0. Okay, since since the varies from 0 to half, that is nothing but the load is, since for various, since the force varies from 0 to P, because if you see, the initially when the rod is there, you will be not applying any kind of force, and initially gradually you are applying. At final position within the elastic limit, you are going to get the load as P. So now the load is being changed from 0 to P. Which load I have to consider, I don't know. So what I do, I will try to average the load. What is the average of the load? 0 plus P divided by 2. So that is the average load we have got. Now the work done is equal to average load into deformation or displacement. When what is the displacement here happening is nothing but expansion of the rod, which is nothing but also called as the deformation of the rod. What is the deformation? We know. What is the formula for the deformation? Delta L by AE. Delta L by AE. We already know that the deformation formula is nothing but delta L by AE. Therefore, here we are going to substitute P by 2 into delta L, that is equal to PL by AE or sigma L by AE. Sigma L by AE. Since we are having force here, other force is here, this is average force. That's why here instead of using PL by AE, we are here we are using sigma L by E. Okay, here I have already done. P is equal to sigma into A. Okay, clear? So P by 2 into sigma by E into L. But whereas in the place of P, we can write it as sigma A, that we have already written. Sigma into sigma, that is sigma square L A divided by 2E. Therefore the formula is sigma square LA by 2E. But LA is nothing but the volume. LA is nothing but the volume. So sigma square V into 2E. Clear? Done here. So this is the amount of work done. Now if you want to convert again here in terms of strain, here we can write sigma by E is nothing but E. Sigma by E is nothing but strain. Sigma by E is nothing but strain. So that is the reason I am here, instead of writing sigma by E, I am writing here as E, that is nothing but strain. This is your value of strain. Clear? So half into sigma into strain into V. Now what is the area we have understood with respect to strain energy is nothing but half into sigma into sigma into E into V, or strain energy is nothing but sigma square V by 2E. So the strain energy, we have got the formula as strain energy is equal to work done. Strain energy is equal to half into sigma by E into V, that is half into sigma square E by V. You can use any formula, you can use this formula, you can use this formula. So all are for the for strain energy itself. So basing on this, we have derived the formula for strain energy when the load is applied gradually. When the load is applied gradually. So try to memorize this formula. Sigma U is equal to sigma square by 2E into V. Sigma square by 2E into V. If it is modulus of resonance, you can directly write it as sigma square by 2E. Sigma square by 2E. Okay. So this is the first case when the load is applied gradually. Now the second thing is the strain energy when the load is applied suddenly. So when suddenly is nothing but, for example, if you are having something which is carrying by using some kind of chains, or you are using some procliner to lift the load, suddenly when you are trying to move it from one position to other position, it has reached the position. When you are slowly going to unload it, suddenly it falls from your unloading position, means it is getting fall down from that position. So what will be the amount of work done? Similarly here also the workload is nothing but force into deformation. Why this force is fixed force is nothing but this is not gradually. Already we have applied some force. For example, I have taken a stone from one position, I have moved to other position. This stone is having some weight, already fixed weight. It is not gradually increasing. So that is the reason here force we are directly taking as P. But whereas deformation is nothing but the amount of distance or displacement which you are going to obtain. So this work done should be equal to strain energy. We have already obtained with respect to the gradual loads, strain energy U is equal to sigma square by 2E into volume. Now this both the amount, both the stress, both the strain energy and the both the work should be equal. We already know that work done will be equal to strain energy, that is P into delta L is equal to sigma square by 2E into volume, sigma square by 2E into volume. So this P by delta L is nothing but sigma by E into L, where E is the modulus of elasticity into L, that is equal to sigma square by 2E into volume. This E into E gets cancelled. Here one sigma gets cancelled. Therefore P is equal to, here we can write volume is equal to A into L. This L into L will get cancelled. P is equal to sigma A, that also we know, that is nothing but P is equal to 2 into sigma by A. Here sorry, I have made a mistake here, so try to rectify this mistake. I have noticed that. So this is equal to sigma into A divided by 2 will be left out. Sigma into A divided by 2 is left out. So sigma is equal to 2p by A, 2p by A. So with this, what we have understand, we already know that this P sigma by A is nothing but called as stress. So that I am trying to correlate the relationship. Generally what is P by A is nothing but if you are applying the load suddenly, what we say, if you are applying the load gradually, then you are going to get the stress, as that is nothing but P by A is nothing but the stress. So it means that the stress induced suddenly, so this is the stress which is induced in a material because of sudden impact, by sudden loading. But whereas this is the stress, P by A is nothing but the stress which is developed because of gradual loading. With this we can able to correlate the relationship between the sudden loading and gradual loading. That is nothing but the stress induced suddenly in this case is twice the stress induced which is when the same load is applied gradually, because here also P, there also we have taken it as P by 2. So similarly the sudden load is nothing but 2 into gradual loading. Sudden loading means when the crane is lifting the object and bring back to rest. When it is just above the platform, it suddenly falls. Clear? I think very much it is clear. So because this is the only thing we have to do is, here we have to correlate the relationship between the work done and strain energy formula, which is U sigma square by 2E into volume. The next thing is the strain energy stored in a body when it is being impacted. What is impact is nothing but when the load falls from certain height. You are having a load at some certain height, suddenly that load completely falls on an object, that is called as impact. For example, here I am having a thing on which there is some load at some particular height which we have considered as h. There is some collar here. On this collar, this load is falling from a height h onto this object. Because of this height, it is having some potential energy that will be converted to kinetic energy. It will create some impact. So if you take a stone and hit someone, so what is happening, the stone initially was at rest. You might have seen this in a regular time. If there is a wet ground, if you are making a ball which is some height, so with respect to height there will be some impact on the ground. Similarly, as the height increases, there will be more impact on the collar. Because of that reason, we are going to study how the impact force is affecting the strain energy. So we already know that strain energy is nothing but sigma square by 2E into volume. But whereas what is the amount of work done by this load on this material is nothing but work done is equal to load into deformation. But whereas this load is nothing but P, but whereas what is the deformation it will produce is nothing but from because of the height, it is giving some displacement, that is h plus delta L. Since it is falling from some certain height, so that is also considered as the deformation or the displacement. We are having two works done here, that is nothing but P into h, one work done, okay, P into h plus P into deformation. First work is because of the displacement, it is doing some certain amount of work, so that's why I have written directly here P into h plus delta L. Whereas this is the first work done W1. which is because of the displacement. When it is moving from this position to this position, it will do some amount of work which we can consider as W1. Okay, so similarly, because of the loading, it will undergo some deformation, that is called as W2 here. I might be clear here, but you might get confused here without understanding directly how SAR has taken H plus delta L. You might be clear with this. P into H plus P into delta L, that is nothing but W1 plus W2. So work done is equal to strain energy. So that is nothing but this work done should be equal to the strain energy, that is P into H plus, here if you take both the P's are common, so I can take it as H plus delta L, that is equal to sigma square by 2E into AL. Now multiply this P inside this value, that is nothing but PH plus P into delta L. We already know delta L is nothing but sigma L by AE. That is, every time you have to remember that delta L. This whole first chapter is completely based upon your deformation formula. Either you can take it as PL by AE or sigma L by E. PL by AE or sigma L by E. So here we are considering it as sigma L by E into sigma square by 2E into volume is always considered as A into L, that is nothing but area into length of the material. So PH plus P sigma L by E, that is equal to sigma square by 2E into AL. So what is this is nothing but this I am trying to convert in terms of a quadratic equation. So the quadratic equation, if you see here, we are having sigma square, here we are having x square. What is the general quadratic equation form is nothing but ax square, you might have studied this every time, ax square plus bx plus c. So the equation is like ax square plus bx plus c. The further simplicity, what you generally do in quadratic equation is nothing but you try to remove the coefficient of x square so that you can easily solve the equation. That is nothing but you will try to convert it as x square plus b by bx by a, that is nothing but whatever is the coefficient of x, you will try to divide with this other value, that is b by a, okay, plus c by a, correct. You can also try to do like this. Done. So what here I am trying to do is, here I am getting this equation, that is sigma square L by 2E. This values goes on the other side, so this will become minus, this will also go on other side, this will also become minus, is equal to 0. Now I am trying to divide this whole equation with respect to AL by E. Why I am dividing with AL by E is nothing but, if you see, L value is there, E value is there, L value is there, E value is there. So A is only here, so I am trying to divide this equation like this. So this equation will become in this form: sigma square by 2 minus sigma by p by a minus peh by al. Initially it was ph, now it has become divided by e by al, is in the form of an equation ax square plus bx plus c, but where a is nothing but 1 by 2, b is nothing but minus p by a, c is nothing but minus peh by al. Now we already know that when we are having a quadratic equation, if you want to find the roots of the equation, we can find it by x is equal to minus b plus or minus under root of b square minus 4ac by 2a, b square minus 4ac by 2a. Try to inculcate all these b values, a values and c values, minus of minus p by a plus or minus under root of p by a the whole square minus 4 into 1 by 2 into c is minus pe by h into al. So I am trying to inculcate all this a b c values in this formula, generalized formula. So with that you can able to get the answer of sigma as p by a plus under root of p by a of 1 plus under root of 1 plus 2ae by 2aeh by pl, 2aeh by pl. So you try to solve this problem. 2 ones are 2 here, 2 twos are 2 twos are 4 here, again p square, p by a the whole square, here also p by a, here also p by a. So this is not square. If you want to remove it from the square root, this should be square. So how this will become square is nothing but dividing the value with the same value, that is nothing but reciprocal should be written. The reciprocal is nothing but A by P has to be written extra. So that's why I'm writing here A by extra. So P by A is taken out common. So what is left out inside is, in the place of P by A the whole square, 1 will be left out, plus 2 into, in the place of P by A, that should become reciprocal E by A. EH by L is as it is. So whatever the equation you are going to get, that is because of induced stresses due to impact. Now you have to remember these formulas, note them. These formulas are very important. Strain energy is equal to sigma square by 2E into AL. This is the generalized strain energy formula, whereas modulus of resonance is nothing but the strain energy per unit volume. That is nothing but you have to divide this volume or remove this volume, you will get sigma square by 2E. But whereas strain energy due to gradual applied loading is also same, sigma square by 2E into L. But whereas when the strain energy is stored in an object, so but whereas you hear this energy, this sigma is because of gradual loading. So strain energy stored in an object when sudden load is applied is nothing but P sigma sudden should be equal to 2 into sigma gradual. So when the load is applied impact, sigma should be equal to P by A of 1 plus under 1 plus or minus under root of 1 plus 2 EAHL by L. Clear? So with this we have completed the derivations. So we will try to solve one or two problems in this. Then we can able to close our session. So the mild steel rod of 1 meter long and 20 diameter is subjected to an axial pull of 62.5 kilonewton. What is the elongation of the rod when the rod is applied gradual load? Second is sudden load, and they have given the value of Young's modulus E as 200 gigapascal. So try to take the values. One, they have given the length as 1 meter, so we'll convert it into 1000 mm. Every time you have to convert it into mm. So diameter is given as 20 mm. The load is given as 62.5 kilonewton. Kilo is nothing but 10 to the power of 3. E is nothing but they have given as 200 gigapascal. Giga is 10 to the power of 9. But whereas Pascal is Newton per meter square. So to convert into millimeter square, Newton per mm square. I need not to explain this again. I have been explaining this from the first class. So you should be very much careful about this giga, mega, and kilos. Okay, since the load is applied gradually, so we know that delta L is equal to PL by A. Obviously we know that delta L is equal to PL by A. You are going to get P load is applied, L we know the length, area we can able to find when the diameter is given. If it is a diameter, then it is obviously a circular object. What is the area of circle? In nothing but pi by 4 d square, pi by 4 d square, and E is nothing but 200 into 10 to the power of 3, so that you can able to get the gradual deformation which is obtained when a gradual load is given. When we know that when the sudden load is applied, we know that sigma sudden will be equal to 2 into sigma gradual. So what is, because these loads are applied gradually, these loads are applied, they have not told that the load is applied suddenly. Okay, so the load is obviously axial pull is acting, so obviously that load is nothing but a gradual load. So with that we have to calculate the sigma sudden first. So we have calculated the sigma sudden. Once you know the sigma sudden, delta L sudden is nothing but sigma sudden into L by E. We already know what is delta L is nothing but sigma L by E. So sigma sudden into L divided by E. With that you can able to calculate the value of delta L. So with this I try to stop here. In the part 2 lecture, if it is possible, we will have the same lecture today, and we will try to complete about the strain energy. Thank you.